Welcome to Heater Materials Lecture 17. In the last lecture I looked at grey bodies and the radiation exchange between grey bodies and developed an electrical resistance model that can be applied to this particular problem. And I emphasised the fact that that electrical resistance model is not compatible with the electrical resistance model we met earlier in the course. I then looked at applying that model to the measurement of temperature in a gas flow, which is really an example of a small object in a large room in terms of the radiation exchange. What I want to do today is say something about radiation shields, a little bit about participating media and the greenhouse effect, and that will essentially conclude the material that I'm going to cover on heat transfer. Now, as I showed last time, radiative exchange can lead to significant inaccuracies in measuring temperature. So one way we could try to address this would be by using a radiation shield. So if I go back to the example that I looked at last time, you could envisage putting some sort of radiation shield around the centre of this thermocouple that is in the gas flow. So the gas flow is still at 200 centigrade, the pipe wall is at 180 degrees centigrade, convective heat transfer coefficient is the same as before, and the radiation shield has emissivity epsilon s. In this case, the radiative heat transfer from the thermocouple bead can be modelled by 6 resistances in series. So the first resistance deals with the surface resistance of the thermocouple, i.e. the emissivity of the thermocouple. Then we have one dealing with the shape factor for going from the thermocouple to the shield. Then we have the surface resistance of the shield for the incoming radiation. Similarly, on the other side of the shield we have a surface resistance for the outgoing radiation, then a shape factor resistance associated going from the shield to the pipe, and finally surface resistance of the pipe. The endpoint potentials again are the black body terms, one of the shield and one of the pipe. So this is the sum of those resistances, and to simplify this a bit further, we can note the fact that most, or essentially all, of the radiation from the thermocouple bead should reach the shield, assuming the shield is actually really shielding the thermocouple. And secondly, most of the radiation from that shield should then reach the pipe. So in other words, we can set the shape factor going from the thermocouple to the shield equal to 1, and the shape factor going from the shield to the pipe equal to 1. The one other thing just to note in this equation, of course, is this factor of 2 arises simply because these two resistances are identical. Taking into account the shape factors being equal to 1, I can simplify the equation slightly as shown here. And then in the line below, I've shown you the equation I derived last time for when there was no shield present. And by inspection, we can see that the first term is the same in both cases, the second term is the same in both cases, the last term is the same in both cases. So essentially the difference between these two equations are these two terms. And that's why I've written the final result here as RS is being equal to R, i.e. all of this, plus those two additional terms. And then I've just rearranged that very slightly to get this final result shown here. And what that means, if we plot RS minus R multiplied by AS, is you can see that the difference between those two terms becomes very large if the emissivity is very small. In other words, if we want to maximize the resistance to radiative heat flow, we want the emissivity to be as low as possible. The types of materials that we might choose become fairly obvious when we look at this table of data. So for polished metals, you can see that the emissivity tends to be very low, whereas for ceramics, etc., the emissivity tends to be high. So radiation shields will tend to be metallic foils, and really the only thing you're probably going to have to worry about is whether they oxidize to the point that their emissivity goes up significantly. But essentially the ideal thing to choose is some form of metal foil. And if you really then want to reduce the radiative losses still further, you use more than one radiation shield. So you would have layers of metal foil. So if we had N shields, then the resistance network essentially becomes this. So you can see that this term N enters the total resistance, and as n goes up, clearly the total resistance will go up, and therefore the radiative heat transfer will go down. And just as an example, this sort of unit contains 7 layers of aluminized mylar as thermal radiation shields.